Okay, so a couple pages ahead in your notes, we're going to take a moment to define some common wave terms that you'll be dealing with. The amplitude of a wave is the maximum displacement that the wave achieves or produces from the center position or the center line, if you'd like to call it that. And so on a wave shape, if we want to think about the shape of a wave, here's a wave. We measure amplitude from the center line, so from here. We measure it this amount up, or this is the amplitude as well. It's the distance to the maximum displacement. Now, displacement is something that particles have. There are little beads or water molecules or something, some sort of particle, along this medium, and the wave is nothing more than the shape of all of these particles displaced in succession. So when we talk about displacement, we're not really talking about the wave having displacement. Displacement is something that particles have. Okay, what's period of a wave? Well, period has to do with one cycle, so before we try to define it, we need to know what one cycle looks like. Here is one wave cycle. How do I know that's one cycle? Because if I repeat the shape, I get a continuous wave. Okay, but there's another way to draw the wave cycle, and you want to draw these in your notes. Here's the second way we can draw one full cycle. How do I know that's a full cycle? Because if I repeat the shape and I copy it over, I get a continuous repeating wave. The final way to draw a wave cycle is like this, from trough to trough. How do I know that's one full cycle? Well, because if I repeat the shape, I get a continuous wave. So that constitutes a full cycle. These are shapes you have to memorize and be familiar with and comfortable with. All right, let's use that to define period of a wave. Let me pause this first. Look, you can see from here to here, that's one cycle. From trough to trough, that's another way to measure the cycle. Or from here to here is yet another way to measure the cycle. So we know it has to do with the cycle, we know it has to do with time, but what exactly is that time for one cycle? I mean, you can't just look at one cycle occur, because there's lots of cycles on my screen. I see one here, I see a second cycle, another half. So what exactly is this time? There are two ways to measure period. The first way is you can measure how long it takes to produce exactly one cycle or exactly one wave. So let me slow this down. When I get to the top, I'm going to hit start. There's the first crest. See that crest? Let's follow it as it moves across. And at what moment have I finished creating one cycle? Right there. I started here, I ended here. Between those points is one complete cycle. So the period is roughly 2.2. So the period could be the time to produce one new wave cycle. But there's another way to define period. The other way to define period is like this. Let me come up with a reference line here. My ruler there is the reference. I'm going to time how long it takes for one complete cycle to pass this reference line, or to pass this point in space. So I hit start. Let me see. This crest, I'm going to watch this crest go across. When it crosses, okay, there it goes. And now when the next one crosses, 2.2 roughly. Let me do that in slow-mo. So I'm going to start the timer when this cycle begins passing. So here's that cycle. I'm measuring with my cursor. And when has that full cycle finished passing by? Right here. So 2.2, same exact period as before. So we can define period as the time it takes to let's see, no, not complete, that's vague. Complete is vague. The time it takes to produce one complete wave cycle, or the time it takes for one complete wave cycle. Let's see, can I get this forward? Yes. One complete wave cycle to pass a reference line or fixed point in space. That is the definition of period. So you can choose either definition on a test. This would be acceptable, and this would also be acceptable. You could use reference line, you could use fixed point in space. You can choose one of these and write the definition that makes sense to you. Frequency is a really closely related idea. After all, we know that there's this relationship. Frequency is equal to 1 over the period, and vice versa. You can flip those two variables. The equation is still true. So let me give you the definition, and then we will take a look at the simulation. Okay, frequency. Move this over. Frequency is not the time to produce one cycle, but the number of cycles produced per unit time, so per second. And likewise, just like before, there's a second way to define it. The number of cycles that pass a reference line or fixed point in space per unit time, so per second. These are the two definitions. Let's see how they actually work when we look at a simulation. Alright, so I've got my wave traveling through. I'm going to put this, it's already on slow-mo. Wow, this is a fast wave. I'm going to watch how many cycles are produced in exactly 1 second. So I need to start when it gets to the top, and then I'll count the number of cycles that we make. Go. Oh, I was late. Hang on, let me try that again. Oh gosh. Here's what I'm going to do. See how we're right at the top? I'm going to hit play. And I'm going to, so I've started the clock, but I'm paused. So let me unpause. Okay, that's 1 full cycle. We started here. We made 1 full wave cycle, and 0.33 seconds have elapsed. So I let another one go. Okay, there's 2 cycles. We're almost at a second. So I'm going to go step forward. There's a lot of clicks. Maybe I started clicking too early. Okay, in 1 second, we made 2. We're on the third. So what is that, 2.9? Yeah, the frequency is 2.9, because look, it says right there, 2.9, 2.89. So it's the number of cycles that we produce per 1 second. I could also do it by watching how many cycles pass a point in space, but I'm not going to show that to you. I think the concept here is clear enough. On to wavelength. This is an easy idea. Before we write the definition, let's draw a, this is a transverse wave, and then we'll also draw a longitudinal wave. So there's a compression, there's a rarefaction, there's a compression, there's a rarefaction, compression, and so forth. Okay. 1 wavelength is the distance from crest to crest. That's the wavelength. We use the Greek letter lambda for wavelength, but you can also measure it from trough to trough. Or if you want, you can measure it from the center to center. These are all the same wavelength. And on these kinds of waves, longitudinal, you can measure the wavelength from compression to compression, or you can measure from center of rarefaction, right here, to center of rarefaction, and it's the same length. They have the same wavelength. So what definition can we write which captures crest to crest, trough to trough, middle to middle, rarefaction to rarefaction, compression to compression? What single definition can we write? Here it is. A wavelength is the distance between 2 points that are in phase, we're going to say, on successive waves. So 2 in-phase points, that's the crucial term. When we say 2 in-phase points, we mean we're at the same part of the cycle. You're measuring from crest to the next crest because they're both crests. They're at the same phase or stage of cycle. Or you can measure from trough to trough because they're both troughs. They're at the same phase or the same stage of the cycle. And likewise, you can measure from compression to compression because they're both compressions. They're the same phase, the same stage in that repeating cycle. Okay, on to wave speed. This is a different concept from particle speed. Let's take a look. There are two things moving in the simulation. There are the particles, like you see this green particle going up and down. Just that green particle right there, going up and down. Let's zoom in. Up, down, up, down. Oh gosh, we're all going to get dizzy. In addition to particles, there is this crest traveling across. Here's the crest moving across the screen. My mouse is showing. And now there's another crest traveling all the way across the screen. So which is going faster, the particles on average or the crests? Well, the crests are going quite slow. They don't progress forward very quickly. The particles, on the other hand, are going up and down really fast. So there is a difference between the average particle speed and the wave speed. Wave speed is the speed at which energy propagates forward through a medium. Now, this might sound a little like a definition for power, right? Because power is the rate at which, 1 over delta T, the rate at which work is done or energy is converted or transformed or exchanged. But this is not what we mean by wave speed. We're not talking about power. We mean literally how many meters per second does the energy travel forward. That's what we mean by wave speed. Okay, damping we've seen. Damping is a reduction in amplitude due to energy loss. What causes damping? Friction, of course. So we can say it's caused by friction.